Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So we talked a lot in the warm months about warm weather stuff. And now it's getting to be cold months. And there's cold weather stuff. And I realized there's like a little commonality between these two things. So in the summer, you grill. And in the winter, you have like a campfire or a like fire in your hearth. And when you light something on fire, at least wood or charcoal, like it kind of gets like black and like burned up. But then if you have like the ashes left in the pit at the bottom, like it's all white, kind of like ghosty gray. And I don't know why that is. I don't know why like, something that burned up and is black then like burned up again, like bonus burning up and then turned white. I don't actually understand like what's happening there. Is it the ghost? Are ashes like log ghosts? That could be.
Yes, the ghost of Christmas logs. Well, darn it, Lions. I am a chemist, not a arborist. Yeah.
Arborist.
Yeah, right. Yeah, okay. But with my very limited knowledge and very limited expertise, I will attempt to opine to this. So let's stick with wood for now, just because charcoal is kind of its own thing that's like an offshoot. So we'll just focus on wood, and charcoal is like pre-burned wood. So with that in mind, let's talk about combustion in general. Tell me everything you know about chemical combustion.
Just lay it all out there.
Yeah.
So when you need, you need oxygen for combustion, right?
Mm-hmm.
You need a fuel source, which would be the wood in this case. A rich hardwood, and an ignition source. I think.
Yep.
Right. So which is like the starting energy, I guess.
Yes. Yeah. It's the thing that kind of catalyzes it, right? That like gets you over that initial hump to start the combustion, and then that energy fuels the starting conditions for the remainder, if that kind of makes sense, you know?
Okay. I'm going to do something that I suspect I'm about to super regret, but I think I remember you explaining during another one of our conversations that a catalyst is not consumed in the reaction. And since energy can't be created or destroyed, only transformed, doesn't that mean energy could be a catalyst?
I might have misused the word catalyst there, but basically is that if you have reactant A going to product B, in order for it to go from A to B, it has to hit a transition state, and that transition state tends to be of higher energy than A or B. So you need a little bit of energy to get it over that hump, and then it just whoom goes down, right? So the ignition source gets that first little bit over that initial hump, and then the energy that's being released from going to A to B serves as the starting energy for the remainder of it, and then it kind of self Ouroboroses.
See, this is why I come to you with this stuff, because a Reuter scientist would have been like, "That's not what a catalyst is, dummy."
So let's not worry about the ignition source for now, right? Let's just worry about the fuel source and the oxygen, right? So, generally speaking, in combustion, what are the reactants and what are the products?
Okay, so the reactants, I guess, would be the wood and the oxygen are reacting together.
Right, and what's the main thing that the wood has that's reacting, like in terms of atoms?
Carbon?
Mm-hmm.
Yeah.
Yep. Yeah, carbon and hydrogen, basically.
Oh,
right?
Yeah, sure. Yeah.
Yeah, so it's got carbon and it's got a ton of it because it's got cells, and those are made out of carbon and hydrogen, and amino acids, which are made out of carbon and hydrogen, and other stuff. But basically, when you're talking about general combustion, is you've got something that's carbon and hydrogen. Yep, keep going.
Yep. Okay, so those either separately or together, I guess, are reacting with the oxygen, which would give you, I don't know, CO2, right? So you have you have the like a carbon dioxide gas. I guess some water vapor, hydrogen and oxygen.
Yeah, because you got to get hydrogen's got to go somewhere.
Yeah, and nobody puts hydrogen in a corner.
Yeah, I mean, you started off with hydrogen and the reactants. It's got to go into the product somehow, and water. Yep.
And then I guess the fire part of fire would be like the energy that it's generated by that reaction. Yeah.
Right. That's the energy that's released. It's exciting.
Does that count as a product? Is the energy a product of the reaction, or is that you count that separate?
Yeah. So that the energy is technically a product because it's exothermic, and so it releases energy into the surroundings as part of the process. But yes, perfect. Nailed it. Got it in one. Well done. You see, you don't even need me for this. So yes, and actually, as part of the one of the other little things I wanted to touch on as we were discussing this is that's also in part why you hear snapping and crackling when a fire is going, is because there's a ton of heat, which is one of the products that's being given off, right? And so you'll notice that if you throw like dried firewood onto a fire, it doesn't snap and crackle as much as if you throw like a something like a tree branch that was recently cut down. That'll snap and crackle like crazy because it's actually boiling the water. It's popcorn. It's boiling the water that's in the tree. And then once it gets hot enough, it pops out and it pops, which I think is kind of neat. So you got it, right? So the thing that's interesting is that as the combustion reaction continues to go on, carbon is just carbon. What color is that?
Black?
Yeah, right. Yeah, because it's carbon. It's soot, right?
Right.
That's basically elemental carbon, right? And like if you arrange it different ways, you can get things like diamonds and graphite. But yeah, carbon in and of itself is black, right? So if you keep burning the wood, so the wood is, like I said, like it's a biological thing. It's got a ton of carbon, and then it's got oxygen and nitrogen and all of these other things in it, right? But as you're burning it away, you start to destroy the structure, right? Because chemistry doesn't care. It doesn't care what you want. It just cares about what the easiest, lowest energy thing is to do. So now that it has a ton of extra energy, since you've poured energy into the system, it's got a bunch to work with. It's like, cells, why do that? I can just break all this stuff down. And it does until it eventually leaves behind carbon, which is black. But then, and that's why, you have charcoal, which is basically just carbon bricks, right? But then it gets weird because then it turns to white, right? So I'm curious because I honestly didn't get this when I was guessing. What do you think the white stuff actually is?
Okay, so you could have a process where the end result is like a carbon, hydrogen, oxygen molecule that happens to be white visually, right?
Yep.
You could be in a situation where the carbon, which appears black, has all been burned away, and the thing you're left with happens to be white, right? The ghost of the wood.
Yeah.
Are there other things I could think of? There could be I think the word I'm looking for is contaminants. So like other things because air is a lot of oxygen, but it's a whole bunch of other stuff. So maybe you end up with like a nitrogen, carbon, hydrogen thing, and that happens to look white instead of black. So like other stuff is being left from the chemistry being a sloppy bitch.
It is that.
I feel like those three like categories of solutions are all of the obvious ones I could think of.
Yeah, and actually you did get it correct, which is it is option 2. There is something else there that once all of the carbon's been burned away remains. So figure a fire's pretty hot, right? So anything that is even volatile or semi-volatile is going to be burned away into the atmosphere, right? So that's not going to hang around. So what? And I'll see if with this leading question if you can get it. What would be remaining that is not volatile or semi-volatile? Like what would be the thing that's left behind? Or things. I guess it's not a thing, it's many things.
From a starting source of wood?
Yeah.
I mean, I'm trying to think.
It's fine if you don't know.
Yeah, I'm just trying to because anything organic I would expect to get burned away, right? So like the cellulose and all that stuff, like in the things that make the woody wood. Yeah, man, I don't know.
Calcium, potassium, magnesium, phosphorus, manganese, zinc, copper, boron, and sulfur. It's
Why are
the
those
metals.
things in wood?
Because they're in all living things.
Oh, right. Yes, in
Right.
trace amounts. Oh, man.
In trace amounts.
Damn
right?
it, Full Metal Alchemist.
Right, because that's the thing is that, like, living cells have like a sodium potassium pump, right? It's a small amount of sodium and potassium, but it's there. And to your point, once you burn away everything else, that's what's left, right? Interestingly, there is some carbon that's left behind, but it's been so heavily oxidized that it actually becomes carbonate that then bonds with the salt, right? So ratios tend to be carbon between 5 to 30%, calcium between 7 to 33%, potassium 3 to 10%, and then magnesium, manganese, phosphorus, and sodium all at about like 1 to 0 to 1%, somewhere in there.
I never would have made the connection, but I had the raw facts to have stitched this together because I knew that potash was like a critical invention in human history. Like when we discovered potash, we were able to do agricultural stuff that would have otherwise been impossible because we had a way to distill potassium that we could use to then go do like agriculture stuff. So I knew that from like a social sciences like I'd seen like a YouTube video or something somewhere about that, but it didn't occur to me like, so if there is potassium left over when the wood is burning, obviously that it must have been in the wood to start with, because if you had a potassium salt shaker, then you wouldn't have needed to burn the wood.
Yep. Yeah, but I thought that was like really kind of cool, where it's to me, to your point of Full Metal Alchemist, right, it is such a in my opinion, beautiful exemplar of the law of the conservation of mass, right? Is you account for everything. And there are some things in living things that don't combust and are heavy enough that they're not volatile. And that gets left behind. And that tends to be white, especially like magnesium. It's absolutely white. That's what causes like hard water. Calcium, absolutely white. It's what causes hard water. And so you're like, oh, well, yeah, no, that makes sense. And the idea, and that's why you only get those when you have completely burned the log. You completely combusted it, right? So like if it's just singed, it'll turn black, but when you've completely burned all of the other carbon away in this beautiful crucible of the fire, you are left only with the heavy metals that were used to continue to keep the chemical processes alive. And that has a degree of poetry and beauty for me as a chemist, and I think that's kind of cool.
I think there is something here that you could use to like screen for like curiosity in children, because if you had a fire going and then it like burned down and it was just white, and it was like, hey, you all saw me put the logs on the fire, and then you all saw me start the fire, and now the fire is burned down and there's this white ash left. Why is it white? Why isn't it black? And they wouldn't presumably figure it out, right? And you say to them, well, only the metals are left. The kid who goes, but you burned wood, it's like, okay, you come with me. We're gonna go do some experiments in the lab, because you put together, like, at no point did I add metal in an obvious way, but the metal was there in the wood, and now that the wood is gone, only the metals are left.
Yes, only the metals remain. And actually, interestingly, that's how this question came to me, because I was sitting in front of a fire with my kids, and Teddy was like, why does the wood turn white? And I was like, here's my guess. And I rattled off as I'm guessing that the carbon gets sufficiently oxidized to where it turns white, which was technically correct, because the carbonate is an oxidized form of carbon and is still one of the heavier properties of the ash. But that's just me being pedantic and trying to save my butt. Like, I was like, it's really more the calcium, potassium, and magnesium. And the other thing I'll say on this that I got a huge kick out of was, in order to prepare for this episode, I looked up just some more stuff about wood ash to kind of like make sure I'm on the right track and that I'm understanding it correctly. In the current, as of today's Wikipedia article for wood ash, it says, for elemental analysis, typically wood ash contains the following major elements, and it listed them as I did. There is a note that says clarification needed. And it says what the ambiguous percent stand for. Is it mass volume or mole fraction? Readers have no ability to read the writer's mind, and what the writer must not assume that all readers are experts in this field. Using ambiguous units like percent and ppm confuses and frustrates readers who are not experts in this field. Please clear this jargon. And I was like... And I like that level of passion in scientific articles, but it's true. It doesn't say like it's percent of what, you know? But I would assume it's a mass fraction would be my assumption, not a mole fraction, because you'd only do that if you were like doing chemistry and it'd be kind of a pain to measure. But they make a fair point, you know, percent of what?
And see, this is why Wikipedia is a treasure, because there's no profit to be made on Wikipedia, right? You're not selling ads. There's no, I guess, notoriety, but like there's no literal money to be made by being a pedantic Wikipedia editor, which means you're just going to have nerds arguing until they get closer and closer and closer to the truth. And then we all get to benefit because they couldn't let someone be wrong on the internet. Like that is the machine working in a way that benefits society.
You know what? And this may be a bit of a jump, but it's like somebody said, okay, we're going to take the safeties. What if we took the idea of the Safety Goggles podcast and scaled it up to millions of people, right? Just everyone working to burn away all the detritus, like a good amount of curiosity, a good amount of subject matter experts, and they're all just kind of working together. And sometimes they argue, and sometimes they get it a little bit wrong, you know. But like, yeah, it's Wikipedia really is a treasure. But yeah, no, it's I really appreciate it because I saw the percents and I was like, oh yeah, probably mass percent would be my guess, you know. And I saw clarification. I'm like, oh, I wonder if they have the same issue I do. I'm like, passionately, they have the same problem that I do.
They care. Very much so.
Yeah, perhaps too much.
And well, this puts me in a jolly mood to maybe think of some other winter-themed questions I could ask you about.